Okay, thank you for the introduction. And at first, thanks for the committee to give me this opportunity to introduce our recent job. Our recent job is about potential roots of deep sub-area heavy and fusion hindrance phenomenon within the sudden approximation approach. And I'm PV1, and this work was finished at Joint Institute for Nuclear Research at Dubna, and it's a collaboration of China Institute of Atomic Energy and Dubna and also Poland. And my talk contains four parts. At first, I will make an introduction on deep sub-barrier fusion hindrance phenomenon. Then we talk about our modified coupled channel theoretical framework. Then it's results and discussions. Finally, it's summary and perspective. And first, let's see the first part. Since the deep sub-barrier fusion hindrance is defined relative to the coupled channel calculation, which means to calculate the tunneling probability. It's related to model. So let's start from how to calculate the tunneling probability. For the time-independent sub-barrier quantum tunneling, there are generally two ways to get the tunneling probability. And the first is the semi-classical method like WKB, and the formula is like this, and it's the integral of this part, and to get the tunneling probability from the two turning point. And another way, often used way to solve the Schrödinger equation under certain boundary conditions. So this equation can get phi and assume that, for example, this is the potential, and at the potential minimum, there are strong absorptions. There are tunneling waves, only tunneling waves at the left side, and then by comparing the tunneling flux and the incident flux, so we can get the tunneling probability and the reflection probability. Deep sub-barrier fusion hindrance is discovered relative to coupled channel calculation. The coupled channel calculation compared to this single channel is because it has a coupled potential. At first, let's see these two energy level examples. If there are two levels, the Schrödinger equation can be written like this. And if we set Fr equal to this one, then we can solve the equation, diagonalize this one, and get the lambda eigenenergy. And if epsilon1 is equal to 0, then lambda equal to this one, and the tunneling probability will be like this. The meaning of this is like the dashed line is the original potential, and the solid line to line are this part and this part. This amount to the single channel calculation split into two potential, split to the superposition of two potential tunnelings, and the tunneling probability will be also the sum of its two potentials. At some barrier, there will be huge enhancement. This is in linear scale, and in logarithmic scale, the cross section will also have large enhancement, and as well as the angular momentum distribution. So this is the meaning of the coupled channel. With couplings, the sub-barrier will be enhancement. And for multi-channel problem, for the realistic problem, this V is complex, and in CC4 model published by Professor Hagino, for all the couplings are considered, this model was very successful and have been widely used. And before 2002, it can employ many features of fusion cross sections and the mean angular momentum distribution and the barrier distribution, which is called the fingerprint of the fusion cross section. before 2002, the fusion cross-section is measured down to 10 to -2, and the general feature can be described quite well. And after 2002, first measured by Argonne National Library, they found that this reaction is from this paper, and they found that the coupled channel calculation, no matter how did you adjust the potential parameters, the calculations are always higher than experimental data. Therefore, it's called the deep sub-barrier fusion hindrance. The hindrance is compared to the CC calculation and the suction potential. And this word coming from this paper, comes from this paper. And after 2002, there are many experimental data in Argonne National Library and also Australian National University, and also infant experiments. These are just a few examples. Due to the deep sub-barrier fusion hindrance is related to the S factor. The astrophysical S factor is equal to this one, and this eta is Summerfield parameter. One can see the cross-section is related to the S factor, and in astrophysical environment, the reaction rate is related to the S factor. Due to the Boltzmann distribution, and this factor has only influence at a low energy. There will be a gamma window. So the deep sub-barrier fusion hindrance of light reaction system is important for reactions in astrophysical environment. For example, in this paper, they talk about carbon fusion and its influence for reaction rate for carbon burning. And in this paper in 2014, talk about this reaction. And this reaction is also important for study of the stellar evolution. If there are fusion hindrance, then the sigma will decrease much steeper than its original sink. So there will be, it's always accompanied with a maximum of this S factor. So this is an hot topic to study. After the discovery of deep sub-barrier fusion hindrance, there are many explanations, and according to the potential, they can be separated into two schools. First is the adiabatical potential. They assume the potential will behave like this, and the second school is sudden potential behave like this. And for the adiabatic potential, one could see Professor Ishikawa, Hagino, and Iwamoto's many paper. They assume an actual one-dimensional adiabatic potential after the contact of the reacting nuclei, and consider the formation of the complete system. And many reactions, including this one we just mentioned, they can describe quite well. And recently, in 2018, and Professor Hagino also proposed a two suction potential method with different slopes at this part near barrier, and at the deep sub-barrier, also another suction potential to explain the data. And for the sudden approximation and the shallow potentials, one could see the most widely used method is from Professor Misil and Espenson. First introduced in this paper. The title of this paper is Hindrance of Heavy ion fusion due to nuclear instability. They start from nuclear instability probability to get determine the double folding potential or repulsive core plus M3Y forces. For example, for this reaction, this dotted line is AW potential. This is the most widely used non-free parameter potential, and this is the new potential. They can also describe many data. However, in 2017, Professor Simonel, and use density constrained time-dependent Hartree-Fock model and to describe deep subbarrier fusion hindrance, and concluded that it can't be justified by incompressibility. Means this work, and it's more likely to simulate other effects such as Pauli repulsion. So this mechanism and also other mechanism for deep subbarrier fusion hindrance is still debatable. And also instant yes in Dubna, Sajidjian proposed extended quantum diffusion approach plus double folding potential. They get a simple formula which can also explain many deep subbarrier fusion hindrance or light reactions. So in summary, the mechanisms are still unclear and there are lots of work to do. Except the deep subbarrier hindrance, there are often appear another problem is the instability of the coupled channel model. For example, in the same paper of Simonel, it's written that for shallow pocket potentials, the IWBC means incoming wave boundary condition, which is used in the 64 model, should be replaced by an imaginary potential at the potential pocket to avoid the nuclear instabilities. And the nuclear instabilities can be seen like this. This is calculated by the coupled channel 64 code, and one can see there are large fluctuations. So summary, there are some open questions for the deep subbarrier fusion hindrance. At first, whether the coupled channel calculations could be stable at the deep subbarrier region. We can see in previous mentioned work, they use an actual imaginary potential around the potential minimum. However, one had to add more free parameters to introduce this. And the second question is the suction potential enough to describe the deep subbarrier fusion hindrance? And it said in previous work, in almost all of the previous work, it said it's not able to describe it. And they developed a hybrid potential model and other reaction mechanisms. And the third question is what's the mechanism of fusion hindrance, the shallow potential or deep potential? And by this work, we try to answer its three questions. Then it's a theoretical framework. For the coupled channel equation approach, there are several important parts to construct this approach. At first, it's nuclear potential. In this work, we choose simple suction potential, and then it's a coupled potential related to for other coupling, linear coupling, or quadratic coupling. Then it's the boundary condition. There are usually two kinds of boundary conditions: regular boundary condition for complex potential, and also incoming wave boundary condition. Then it's a numerical method. Almost all previous work use finite difference method, like modified numerals, and 3-point difference method, and recently in Dubna, Wieniawski's group, Professor Wieniawski's group developed the finite element method, and there are also a matrix method to solve this problem. In this work, we will use this one. At first, the nuclear potential, we use this suction potential. We start with AW potential because this potential has no free parameters and are widely used for medium heavy reactions. And it's obtained by fitting many elastic scatterings to get the parameter. And for some reactions, this potential can't be applied. Then we start from this potential to fit by minute program. Then it's a coupling potential. Coupling potential will adopt the same method as the CC4 code, like Professor Hagino introduced in this paper. and its nuclear capital Hamiltonian is generated by changing the potential radius to a dynamic operator. It's treated as a harmonic oscillator, adding on the potential radius, and then diagonalize this matrix, and then the nuclear coupled matrix can be obtained by this way, taking the four orders. And then it's incoming wave boundary condition. For the 64 code, they usually use the incoming wave boundary condition at RMIN is usually set as the potential minimum. At the left, when the radius is smaller than this one, then it's a plane wave. At Rmax, which is a large enough distance, it's the Coulomb outgoing wave function. For this case, defined as this one, and this have a serious problem at some situation which have been pointed out in these two papers, because K is related to only to VNN, which means the diagonal part of the coupled matrix. In fact, this requires of diagonal matrix elements tend to 0. However, at RMIN, the distance between two nuclei is very short, and they can't be 0. They are usually large values, and there can be sudden non-continuous changes in the left boundary. So we adopt a linear transformation to solve these non-continuous changes in the left boundary. This KNTPB is developed in Dubna. It's a control Rowe boundary value problem, and it's a finite element method. The updated version we used is like this. At first, it's a couple channel Schrödinger equation. Then we make then let W be the symmetrical matrix of this dimension, and then rewrite the Schrödinger equation as this one. And then at the left boundary, we make a diagonalization, and then we solve the uncoupled equation at the left boundary to get the linear combinations of linear independent solutions. And in this way, the off-diagonal matrix elements have been considered in the calculation. Then we obtain the new incoming wave boundary condition, and the tunneling probability can be expressed as this one. It's tunneling amplitude, and tunneling probability is the square. It's given by summation over all possible states. The finite element method introduced in this work is very high accuracy. It can fulfill this equation fulfilled up to 10 significant digits. This is very important in the fitting process, because the numerous method sometimes met another nuclear numerical instability problems. With this high accuracy procedure, we can fit more stable, and although it takes more time, but it's more stable and reliable. Next, let's see the results and discussions. At first, let's see the oxygen 16 and the summary 144. We try this reaction because it's the reaction which the theoretical calculation is published in this paper. And the full data is published, so we can compare to as a benchmark calculation of a new method. For this reaction, the potential is like this, and the minimum energy is 55 MeV. To consider that is at here, and it's far from the potential minimum. Therefore, the new method does not influence too much. Let's see the diagonal elements at here before and after. They do not change too much. And this is the tunneling probability and the fusion cross sections at the linearization and the logarithmic scale. The first is the tunneling probability. We can see the dotted line is the new calculation. The solid line is the original calculation by modified numerous methods in the coupled channel code 64. You can see in linearization scale and the logarithmic scale, the results are all the same, and also the cross section. So we can say this method is available for this calculation. In this benchmark calculation, there are two levels considered. And next, let's see this reaction, sulfur 32 and this one. And for this, we considered much more coupled levels. This result is published in this paper by Professor Winitsky. And this is a scan plot of this O matrix at RMIN. One can see at RMIN, there are many non-diagonal elements. And the potential is, radial potential is like this. And the diagonal, originally, the coupled channel method consider only the diagonal part. And in this work, we make a diagonalization of this part. And the new boundary condition at RMIN is like this. So we can see the channels, the closed channel and open channel change very much. And this potential is relatively shallow. It can be predicted that there can be obviously difference between these two methods. For example, this solid line is a new calculation and the dotted line is the original calculation. And as well as this reaction, it's the similar mechanism. Next, let's see the deep sub-barrier fusion hindrance. This is one typical reactions measured in this paper by Argonne National Library. At that time, they have tried different kind of coupled channel calculations. However, one can see it's concluded that one can see that the coupled channel calculations are always higher than the experimental data at here. Clearly there is a deep sub-barrier hindrance, and it's concluded that it's very unlikely any minor adjustment in the coupled channel calculation would reproduce the steep fall off of the data at extreme sub-barrier energies, and it appears the fusion hindrance behavior. At here, the coupled channel calculation is with suction potential. And after that, in 2006, as we mentioned, they published a paper by using M3Y plus repulsion potential. And they used this potential to explain this fusion data. The red line is like this, is the results published in this paper. The general trend can be described. And later in 2015, Professor Kapov in Florida Library of Dubna, they can also describe the experimental data, but to only this point. They didn't publish to the lower, so it's not clear what they will be. If at here we show the fusion cross sections, and if we transform them into the astrophysical S factor, one can see like this. And here the calculations fluctuation is not clear, but here there can be seen obviously oscillations, and also for these reactions by using M3Y plus repulsion potential. They used this potential. This dashed line is the result, and this solid line is an empirical calculation with some simple formula. And the standard CC is like this one. This figure is comes from this paper. And later, in 2018, as we mentioned before, Professor Hagino used two kinds of suction potential. At the first one is at near barrier with this one, and then at the deep sub barrier use another one with another type of suction potential with two different kind of diffuseness parameters. They can explain the experimental data of this reaction and also the S factor and also this one and corresponding S factor. Next is all calculations. At first, let's see the red dotted line or dashed line is a new method. The solid line is calculated by original couple channel code CC4. As we can see, the dashed line is very continuous. There is few fluctuations, and as contrast, the original calculation show fluctuations. And in this calculation, we use only the AW potential with no free parameters, and it's coincidentally the theoretical calculation by a new method agree with the experimental data very well. And the original calculation, they have fluctuations below 130 MeV. The reason why, one of the reasons why they have fluctuation below this energy is because we see this green line, the diagonal elements at the diagonal elements, the threshold energy of the original method is lies below 132 MeV. Thus, when energy is smaller than S energy, it will be largely influenced by its elements. And since they didn't consider the role of the non-diagonal elements, so they will be hugely influenced by this. And after diagonalization, a new method can be stable and seems agree with experimental data well. Next is this reactions. It's sulfur 36 and calcium 48 at deep barrier energy. This is measured in this paper. And also in this paper, they use M3Y plus repulsion potential to describe the data. As one can see from this figure, the suction potential always higher than experimental data show the hindrance feature. And they use this type of potential, the M3Y plus repulsion potential, they can describe the data. But they also introduce a weak imaginary potential to eliminate some unwanted fluctuations. This is written in this paper. And this is a new calculation. We use the solid dashed line. No, the dashed line is all calculations. One could see that the dashed line is continuous, and the original calculation, the solid line have fluctuations below around 40 MeV. We can see this figure is a zoom of this part. Below around 39 MeV, there will be fluctuations. One of the reasons is similar to the previous reactions we mentioned. Is because the threshold energy they concentrate at here, and by considering the role of non-diagonal elements, one can solve this unstable problem at this energy region. From this figure, we can see the agreement with the theoretical calculation and the experimental data, and there are still a large part because this part is sensitive to deep sub-barrier fusion hindrance. Next, we fit with different channels with 3 parameter suction potential, and with one could see the solid line is a W potential, the standard potential, and with different potentials and different channels, we can all fit the experimental data. And the parameters that, for example, the diffuseness parameter are all close to the standard potential. And this is the results. They can all describe the experimental data of these reactions. Which demonstrate the results, the idea introduced in this paper. By changing the potential minimum, they have huge influence on the deep sub-barrier cross sections. Next is our results of its three reactions. For its three reactions, we have mentioned before, other people have used, other group have used M3Y plus repulsive potential to describe the data, or Professor Hakino have used two kind of suction potential to describe the data. And we, in this paper, we use the most simple 3-parameter suction potential, and we fit the experimental results with different couplings. And for this reaction, we use only we didn't fit the parameters. The standard AW potential could describe quite well. And for these two reactions, we fit with 3-parameter potential, means the potential depth and the diffuseness and the radius of the potential. And the deep sub-barrier cross sections and the S factor can be described quite well. The error and here means the potential minimum. For this reaction, we also plot the theoretical calculations and the different kind of couplings. For example, this dotted line is the single channel calculation, which means there's no couplings. And then we add the couplings. One can see the sub-barrier enhancement. The amplitude is gradually larger. And if we plot that factor, one could see that they all have maximum at around the same energy near the potential minimum. And even the single channel calculation have this have the maximum of this S factor. Which we can see more clearly from the potential details. And this is the fitted potential of the previous three mentioned reactions. And this is S factor with diagonalization and without diagonalization. It can be seen clearly that with diagonalization, the S factor can be described very well with the standard AW potential, and without diagonalization, there can be fluctuations and far from the experimental data. And if we plot the mean angular momentum, one could see that if there is single couplings, this arrows means the barrier, Coulomb barrier. This arrow means the potential minimum. For the single channel calculation, there are obviously there are three stages. Above barrier, the angular momentum increase linearly with energy, and at some barrier, they are most steady. And when the energy close to the minimum, since the inciting energy can be smaller than the minimum, and the angular momentum tend to 0 for shallow potentials. And when there are couplings, the barrier has kind of distribution. This obscures the mean angular momentum distribution. It behaves like this, but at the potential minimum, they also fall down. This figure is similar to that in this paper. In this paper, they compare the experimental data of these reactions with different kind of potential method. For the sudden potential, which is similar to our work, it decreased to 0. And for the adiabatical potential, since there is no potential minimum, the angular momentum, mean angular momentum keeps steady, and therefore the mean angular momentum could be used the probe to separate its two mechanisms of adiabatical potential like this and the sudden potential like this. Next, we studied the carbon fusion. For carbon fusion, since it's a hot topic, one of the most important fusion reactions in astrophysical environment. There are many studies, and the experimental data were very large. This figure is from this paper, and in our work, we fit the fusion cross section in this paper, and as we can see, the fusion cross section can be described well. For the S factors, we can describe the general trend. Its two colors are the physical review letter paper published in 2020. We can only describe the general trend and here. And this is similar to this sudden calculation. It's M3Y plus repulsion potential. For its resonance potential, in 2018, Professor Diaz Torres' time-dependent tunneling method could reproduce its resonance, and this seems important. In the next, we have also studied this reaction. This reaction is measured in 2010. As one can see, the standard AW potential still could not describe the data. And even if one adjusts the diffusing parameter to 0.9, the cross section, they improve the calculation, but still far from the experimental data. And in our preliminary calculation, we fit the 3 parameter suction potential. We use the normal diffusing parameters. We can fit the experimental data well, and also the S factor and the trend of this slope. Recently, we have also studied. This is also preliminary results of this reaction published in this paper, since it's important to astrophysical stellar evolution. As one can see, the suction potential still have the same problems in previous work, since they didn't consider the non-diagonal elements of at the left boundary. The calculation is like this, and the M3Y potential could describe the data. And again, we could use 3 parameters by considering improved boundary condition. And to describe the data, our potential is not as this shallow, and it's around about 10 MeV higher than this potential. My talk is finished, and then it's a summary. We can answer the questions proposed before in the instruction part. At first, whether could the calculation be stable at a deep sub-barrier energy region? And we could see for several reactions, we could use coupled channel calculation by using the finite element method and improve boundary condition to describe them very stable. And the next question is the suction potential could describe this phenomenon well enough. And as we can see, we have used the most simple 3 parameter suction potential and the multiphonal couplings. We could describe the up to 6 or 7 reactions before. And according to our experience, if the couplings is chosen right, not chosen right, appropriate couplings, they can be fitted quite well. And then the third question was the mechanism of fusion hindrance. As the same idea in previous paper, the mean angular momentum distribution can be used probe to clarify this. for the next step job, because as perspective or next job, next step, at first what's the systematics of the maximum of your hindrance and as factor. We have fitted in Professor Jiang Cheng Li's paper. They have proposed an simple systematics in around 2007 for light reactions. The hindrance is not that strong, and for heavy reactions, the hindrance are relatively strong. And we have fitted several reactions, and we are trying to see more by fitting more reactions to see the systematics. And the next is measure the control which boundary value program is only suitable real potential yet, and our collaborators is working on this method to describe the complex potential and the regular boundary condition. And from the long-term role, we would also like to study the role of other mechanisms like decoherence or transfer and energy dissipation and so on. And my talk is over. Thank you very much for your attention.